to cloud. There we go. Okay, and then share screen. Boom. All righty. Welcome everyone to the BOE Shield bot for Arduino workshop. Today is day one of the 3-day workshop. And we're looking at same time, same station today, Wednesday and Friday. So that's going to be 2 p.m. through 4 p.m. For anybody on the West Coast. And then if you add however many hours of East Coasters will be 5 to 7, Central timers will be 4 to 6, and Mountain timers will be 3 to 5. And so that's 3 2-hour installments. Is everybody okay with that?
Good to go.
All righty. So here we go. This is the Shield bot that hopefully you can see. Can everybody see the Shield bot larger than life on my presentation? Great.
Yes.
All right. So it's a little bit smaller. Well, I guess that depends on your screen size, but at any rate, that's the Shield bot with the last circuit in the book, the infrared circuit. And it's got a pair of wheels up front. It's got a tail wheel in the back, and lots of lessons and motivations and educational opportunities built into the curriculum surrounding it. And let's see here. There we go. So what I wanted to do was show you first just a little bit about what the Shield bot can do. Or rather some of the applications from the stock kit that we sent you out. You might have seen in the slideshow that there were some add-ons, but the first example here is the whisker tactile sensor. So basically there's some whiskers sticking out of the front of the robot, and those are used as contact switches to detect obstacles. Now, there's also photosensitive navigation, which is part of your kit. And so hopefully you can see that somebody turned on a flashlight and started leading the robot around. And that's an example of, so it's in kind of dark, and then there's the flashlight, and it will follow the light faithfully. I forgot to mention navigation, which is has lots of good lessons in and of itself. Navigation, of course, we'll be doing plenty of that on Wednesday, but navigation involves going certain distances, navigating various obstacle courses, geometric shapes like circles, triangles, and rectangles. So there's lots you can do with navigation activities, and physics lessons, for example, distance equals velocity times time is one example. Then infrared navigation, which I mentioned at the start of the session, since that's the circuit that's built on there. And basically, instead of bumping into, and by the way, these are ActivityBot 360 clips, but the same applies to the Shield bot that you have. And so what's happening here is that it's coming up, but it does not have to make contact with the obstacle like it did with the whiskers, and that's important and useful. There's also infrared following, which is pretty neat. It's another, all of these applications where I'm showing you just a real quick clip of something. There are a lot of other applications. And so, for example, you saw infrared being used to avoid an obstacle. And then here, we're actually using infrared with one of the robots to simply avoid the table edge, because its infrared detectors are looking down. And then And then the one behind is using infrared as a crude distance detector to basically follow the robot that's leading it. And one particularly funny thing, I wish I'd gotten it on tape. There was one take of this clip that I did where something didn't go quite right, and the leader robot went off the table, and the follower robot faithfully followed it off the table. It was it would have been great for one of those TV shows where they show humorous videos. Add-on examples like the gripper and line follower and oh, I forgot to add the line follower, I guess. We'll be looking at some of those on Friday. So at any rate, these are great things that you can do with the kit that we sent you, along with learning about circuits, sensors, indicators. Built into the curriculum are lessons that hit check boxes in math, physics, computer science, electronics, engineering, robotics, and there's even music in there. So there's a lot of good stuff, although the emphasis really is in a kind of a CTE computer science pathway. But I will be going much more into the curriculum and the standards on Friday, if that's okay with everybody to wait till then. All righty. So today, what we're going to do is get you a jump start into building your robot. Actually, I'm going to move forward just a little bit and then go back. So today, by the end of the day, what we want to have is this built up. These two black boxes here are servo motors, and they are continuous rotation servo motors, and they basically the Arduino can send them signals to tell them how fast and in what direction to turn. And this is the blue box is the Arduino Shield. And that's where we can connect the servos and also build circuits like these two light emitting diode indicator lights. And then we'll have some batteries connected. And the reason we'll be doing this is because before building the robot, the one really important step is to run a sketch in the Arduino that tells these servos to stay still. And what's going to happen is these servos won't stay exactly still because they need a one-time calibration. And so we're going to do that one-time calibration, which involves a screwdriver, and these guys will be turning slowly, and we'll stick a screwdriver into a little hole in the servo and adjust it until each servo stays still. Then we'll be ready to build it, which will be the homework for the next session. So backing up, that is most of what we're doing Monday. So I'm hoping to add in some simple circuits along with that, along with discussing the homework, any questions that you might have had along the way. So on Wednesday, we'll do some more with circuits, and then we'll also do lots of navigation, and then get started on our first sensor circuit, which is the whisker circuit, where it bumps into something and can tell it and is able to tell that happened and back up and change direction. On Friday, we'll finish off with hopefully a second sensor circuit, and then a curriculum tour, and then also, well, I'm hoping that'll give you a great jump start that you can continue experimenting and prompting your students into further investigation. Let's see here. Okay, so this slide, I believe it's slide 4, is, yes, slide 4 here. I've got a link to this slideshow. There's a PDF version of the book as well as a web book. I'm going to follow this web book link for a minute because I'd like you to see the cover of it. One thing about it is that you can download all the code examples from here. You can also, let's see, there's a pre-written code link. I'm actually going to copy that link, and I would like you to all download the zip file and unzip it. Some of you may have done that for the homework already. So chat, paste, Okay, so that is a shortcut to all the pre-written code with the 2-hour sessions. We're not going to have a lot of time to hand enter code, although that's my favorite way to learn a new language is to hand enter the code examples. And at some point, I'll show you the book on the screen right next to the IDE and actually hand copying the code. But for now, or for most of it, we'll be working with pre-written code. So this is again, I followed the web book link on slide 4, and that's basically the web version of the printed textbook we sent you. And several nice things about this, there's kind of some trade-offs about the web book. For example, if we look at tactile navigation, one thing is that the PDF textbook is going to have some higher resolution pictures for you. But because these web images, they're fine, but they're not really high res. So if you ever need to have something expanded for a presentation, use the PDF textbook to get this picture as opposed to the web version, because this is going to come out a little bit grainy. However, one nice thing about the web textbook is if you're doing assignments, you can actually, copy the link for how whisker switches work, for example. Sorry about that. I just tapped the mic, and put direct links right into the homework as an example of a nice reason to use the web book. I've got links also to the Arduino IDE and the CodeBender license that Parallax uses to teach these classes. If you need your own CodeBender license for Chromebook class, do send an email to education@parallax.com. I will go ahead and give you that email right now. There it is in the chat. And then this is again where we're going today. I'll probably skip the indicator lights. We'll just talk about them, and then if time permits at the end, we'll go ahead and connect them. Little history about these robots. It all started with the basic stamp BOBot, where BOE stands for Board of Education, and it's this large green board on top of this version of the robot. The basic stamp is the microcontroller that the students would write code for. And this became very popular. And as soon as the Arduino came out, which is somewhat about 10 years after the basic stamp, we got a lot of requests to have an Arduino version of the curriculum that we started with the basic stamp. So we did that when the Parallax Propeller came out. That's a microcontroller that we make, as is the basic stamp. We of course did a version of that that's called the ActivityBot, and then most recently we've done it for the BBC microbit, which is very popular because the BBC has given away more than 1 million of those to students all over Great Britain, and so there's a lot of them in circulation. And so we took the microbit, which is right next to the cyber.org logo, and attached it to a board, kind of like you attach the Arduino to a Shield on this one. Any questions so far? Please feel free, everyone, to just kind of unmute yourself and say, hey, Andy, I have a question. This is a small group, so it'll be easy to manage. And also, since I don't have a assistant per se, I might miss something that you put in the chat. So just go ahead and, hey, Andy, me anytime you want.
What was the name of the different processors again? The ActivityBot uses the Propeller, the Shield uses Arduino, the
Yes.
Cyber. What does the Cyber use?
The CyberBot uses the BBC microbit. The microbit's kind of a neat little device because it's got a whole lot of sensors built into it. It's kind of like a microcosm of a cell phone in that, like, it's got some little buttons that you can press built into it. It's got a little light display for showing you messages. Inside it, it has a built-in radio. It has a to allow microbits to communicate with each other on a network. Gosh, what else? It's got a light sensor, temperature, compass, tilt. It allows you to program in a lot of extra things in the robot so that, for example, these two or more robots can all talk to each other with built-in radios without incurring any additional expense. These other guys all would require a peripheral radio module that you'd have to connect and then program it to communicate with them.
And what about the Bobot? What does that use again? It's just called the microprocessor, or?
This green guy right here is called the Basic Stamp microcontroller. It came out in '95 and it's still in use today. It's a really nice design. It's a little bit closer to when you write a program to make these servos turn. You actually, in the program, have to manage repeating the servo control signal 50 times a second, which is required. The rest of these robots down here have built-in ways of controlling servos where you basically use one command, and then the microcontroller in any of these guys jumps in and continues to send whatever signal you ask it for 50 times a second to the servo to keep it moving. So that so this is kind of a lower level coding. You're much closer to the hardware with the Basic Stamp. With all of these, there's a way to you basically tell the servo how fast and in what direction, and then your program can move on to the next thing, which is probably some kind of loop where you're monitoring sensors. So the unique thing about the activity bot is that the processor on here is multi-core. The servos on here have special sensors inside them that allow you to measure a 60 by a 64th of a turn to find out how far and in what direction the wheel is actually turned. And it even has like a built-in control system, so you can do more precise navigation than with these other guys. So there's trade-offs for all the different ones. Also, the language for the Bobot is basic. The language for the Bobot robot is basic. The Arduino is kind of a C++ and a holder, so to speak. It's the C++ language, but they call it the Arduino language, and they hide away or tuck away some of the more technical aspects of setting up a project in C language, so that you can just sit down and start to code as with these others. The activity bot is in Blockly, or yes.
On the C++ comment, is there an easy way to get past that wrapper to get all the way down into the lowest level of that thing for engineering students?
There definitely is a way. There's a bootloader in the Arduino that basically wakes up and checks for an incoming program, and then if none is coming in, it loads the most recent sketch. But I believe it's the Atmel microcontroller that's built into it does have a way for you to delete that bootloader, and then you can use a lower level development environment to get down to the nitty gritty. It's a different API from the Arduino also, but it is a C++ API application. Sorry, I'm throwing around jargon.
It's Microchip bought them up.
Oh, okay.
So now it's called Microchip Studio.
Oh goodness, really? So
Yeah.
You're using that instead of the Atmel Studio? Oh, for goodness sakes! Thanks for the
Atmel Studio became
Microchip Studio. That makes sense. Thank you.
So
Okay.
and we use it for assembler on the AVR.
Oh, hey, that's nice.
Yeah. So teaching the students both ways, going up and going down.
Yes, and I think somebody mentioned that they used the Arduino Playground. It was to get started with some Linux stuff, but I believe that that's also where you would find how to program at the lower level with Microchip Studio. All right, then. Shall we move on? So here's what we have today, and hopefully you've all got this connected currently. If you haven't, go ahead and connect it to your computer, and because you want to be ready to program. First thing I wanted to do is just kind of go over the homework that we assigned, in case there are any questions about, well, gee, I entered a program and I don't really understand why it did what it did is one of the questions I'm hoping for. So I'm going to open up the very first sketch, which was the hello sketch. And it's taking a minute here. Let's see. Bear with me a second. I switched to our office, and so some network protection-y thing jumped in on me that I didn't see from my home network. Okay, hopefully allow access. Okay, I'm back. Can everybody see the print on my screen okay?
Yes.
All right, thank you. So just give me a shout out if it's not clear. And I'm a little uneasy about this. I'm going to go up maybe another couple notches here. That didn't seem to take effect. It will next time I open the Arduino, hopefully. All right, so this was the first installment in your homework, and so we hit the little check mark to compile it, and it told us eventually either that there was some typing mistake or that it was ready to try running the program. So that's what the check mark is. It's let's see, where's the flyover for it? It's not coming up. Oh, there it is. Nope. Yeah, I don't remember the specific word, but you're basically compiling the code. So now it says done compiling, and there's a message talking about how much code space it's using. Then the upload button, which is the arrow next to the check mark, is a way to upload a compiled image of that program to your Arduino. And so it goes ahead and recompiles. You see a little status bar in the lower right, and then it tells you it's done. And in the upper right, there's a serial monitor, and that the relative locations in CodeBender are similar, but give me a shout out if you need a hint on where to find something in CodeBender. So here we have hello, and one important thing to note is that I put those statements, the hey, get ready to talk serial to the computer statement, and the okay, send a hello to the computer, you Arduino send a hello to the computer statement, in what's called in Arduino speak the setup function. So this function is basically set to run once, and then it drops down to the loop function, and anything you add in here happens repeatedly. So what the book does is it tells you, okay, let's take that hello and put it in here, and then we'll see a bunch of hellos, and it'll be kind of not what the student expected, because the hellos will all be chained together one after another. And then the book uses that opportunity to say, okay, well, now that you've seen that, how about if you try the print line, the print ln function, and then what that'll do is that will print hellos down the screen. And hopefully most of you had a chance to try that in the homework. And so what I'm going to do is just mention that this automatically loops because of the, well, I'll just run it. Might switch to CodeBender because the Arduino IDE does take a while to compile this. But here we see, oh, you know what? I kind of overdid it on the frequency of hellos. I think we also added a delay. I forget whether it was 100 or 1,000. Let's do 500. Anybody remember?
I thought it was 1,000.
Oh, 1,000. Okay. Yeah, one thing that can do is kind of when the serial data is streaming in that quickly, especially for those of you who are using CodeBender, I would imagine that there is a risk of maybe overwhelming the serial connection. Don't know for sure, but I always try to put a delay anytime. Now we can see that it's doing it every 1 second. Now, if you're curious about how to find out about stuff like delay or serial print line, what I'd like to do is go back up to the resources slide. That was slide 4. And I put a link to the Arduino reference in there. While writing the textbook, I had this page open pretty much the entire time. And so what it allows you to do is go searching for the various keywords. So for example, I'm on the page. I don't see it straight off the top, so I'm just going to do Control F and type in delay. Ah, there it is under time. So we have delay, and we can go and find out about delay. And so it talks about it, you know, it explains it, shows you the syntax. And what I like about this is that it also gives you a nice little example to see how delay can be used. And so, it's the Arduino reference is a very effective tool for just having on hand to look up stuff as needed. Let's see here. Next up is store and retrieve. Did we do local variables or global variables first on the storing and retrieving? Does anybody remember?
I believe it was local first.
I think so too. And the reason that it's important to make this distinction between local and global. This setup function has something called a scope, which means that if you declare a variable inside the function and set it to some value like 42, this function won't know that value. So for example, if I wanted to repeatedly print that stuff by putting it in the loop function, this would not work because anything up here will know about the fact that I've said a equals 42. But that's because it's inside this function where I said, hey, let's make a variable named a and set it equal to 42. Down here, this is a different function, this loop function, and so it doesn't know about it. So in order to get this to work, if I wanted to do this repeatedly, I would want to make these variables what's called global. So right now, these variables are considered to be local. And if I take them out of that setup function and put them above all the functions, then we're happy because they are now global variables, which means that I could access them at the beginning like this. But again, over here, because the variables are declared up here, which means that it doesn't matter where else they are. They can be accessed inside this function, and they can be accessed inside this function too. And again, please just jump in. And Now, yeah, unfortunately, I don't know why looks like I skipped the storing and retrieving local, or well, basically for some reason I have this example that is simple math, but I named it store and retrieve. So you got a little bit of a mashup there of what the homework was. So this is simple math, and this is part of a lesson where we start with addition and then try out multiplication, division, et cetera, and learn a little bit like division, for example, in the Arduino is an integer thing. So if you say 9 divided by 2, you'll get the answer 4. Well, wait a minute, 2 times 4 is 8. Well, yeah, but in the integer world, that's how many times 2 goes into 9 is 4 times. But you could also say int r for remainder equals a percent b. And that's where you would find that remaining 1 from the division problem. Somebody had technical difficulties. Margaret and anybody else, there will be a recording of this Zoom video that gets posted either later tonight or early tomorrow morning. And so that'll give you an opportunity to, oh no, did I forget to hit the record button?
No, you're recording.
Oh, good.
No,
Oh, that was a terrifying moment.
Record is showing.
I'm sorry?
Record is showing on my screen. So.
Oh, perfect. Okay. So not only will you get to see a YouTube video of this session, you'll get to see the whole session. All right. So we have division and remainder of, and then there's also, all the goodies like plus, minus, and multiply as star. And so that's an introduction into just simple calculations. And by the way, the reason for doing all these things, or rather, there's a little bit of computational thinking going on that I want to make sure that everybody taking the class gets. And we do this in installments, and the first installment is, hey, if the Arduino is new to you, in chapter 1, we're going to talk about the basics of programming, the very basics. So I essentially split that up into communicating, like the hello message, remembering, like declaring a variable and setting it to a value, and then printing that value later. So that's remembering. Calculate is one we just did. And then the two that we have not yet done are decide and repeat. Well, we've done repeat since there's that automatic looping function, but there's also another way to repeat that becomes important later on. For those of you who are looking for other things like arrays and functions, those do get introduced as we go. I also didn't want to send anybody into computer programming saturation mode here. So that's why we just did those 5 basic ideas in programming. So count to 10 is another way to repeat. And then I'm also going to open up simple decisions, see which one comes up first. Okay, so this is count to 10. And then here we have simple decisions. I did decisions before. Let's see, we need to have somebody mute themselves. Oh, thank you. Okay, so here is just basically a really simple decision where, well, actually it's not as simple as it could be, because we have A and B and we've set them to values. And so in the textbook, then since A is greater than B, this will be printed. And this also gives us an opportunity to talk about the if versus the else, so that you can set up some kind of mutually exclusive decision making with this. You could just basically do this and only print something when A is greater than B. But by having else, you can say, well, if it's not greater than B, then, or if it isn't, if A is not greater than B, then let's print A is not greater than B. Another way you can approach this is there's even an else if. Yes, question, hello?
Yeah, no, I'm sorry. What happens if it's equal here? We're gonna have.
Yeah, and so that is also part of the textbooks approach, is to introduce else if. And then we can do A is less than B. And then we can say, I forget exactly how the book did it, but it's something like this.
Close enough.
And then now that we have the else, we can say serial.print A is equal to B. And so that's that lesson. And it gives just a first taste of decision making, which is crucial later on. Let's see here. Here is the other one, count to 10. So in addition to this, this looping, we have another way of repeating stuff, which is not infinite. So this is void loop, is anything you put in here will go repeatedly until you turn off the power to the Arduino. Whereas up here, since this is just a do it once kind of function, everything in here only happens once. So this is going to count to 10 once. And so about this counting to 10, there's a really important aspect here that sometimes gets missed or glossed over or not read by the students, which is this I, and I is short for index. So something that I encourage teachers to do is to expand this a little bit and to actually do stuff like add in serial.print index equals. And then serial print line index. That way they can see that the first time through, the variable is 1. Then the second time through, the variable is 2. And this gets used later because when you want to work with lists, each item in the list has an index. And so there's the 0th item in the list, the first item in the list, the second item in the list. And so having this for loop where the first time through it says, hey, index is 1. So we print index. Then the loop repeats and it says, okay, let's add 1 to index. That's this part, which could be rewritten index equals index plus 1 even. So it increased by 1. Is 1 less than or equal to 10? Yes. So we get to go through again and we see that index is now 2 and then 3 and then 4 and then 5 all the way up till 10. And so that's a very quick summary.
Just a quick question. Is it a comma or a period for the first serial print?
Oh, well, that's probably why it highlighted it and gave me an orange message down below. Thank you. Let's see if it runs now. Still waiting for this little green bar to get to the right edge and the message to appear. After that, I will go ahead and open up the serial monitor. No, it didn't freeze, but I still did something wrong. It's probably because I have the one of my other Arduino IDEs. This is a good thing to talk about too. So I have several instances of the Arduino IDE open. And it looks like maybe one of them has its terminal still open. And so that's probably why it wouldn't let me program it. Okay, we're out of, I think, all the other ones. I'm going to just double check, make sure there's COM40. There's Arduino Uno. We'll try one more time. Okay, it succeeded that time. So now you can see that it says index equals, and then you get each value. And then that way you can see that it's not just to make code repeat itself 10 times, although you could do something like say hello 10 times, but you also have access to which iteration of this for loop has been completed. Are there any questions at this point? Because that was kind of, my hope is that by essentially typing in those code examples, that it kind of sinks in better that way. But I wanted to kind of bring them up and run them all for you, or run a certain number of them for you, and also make a few suggestions as to how to kind of bring it out for the students. And but at this point, I'd really like to make sure that I haven't left anybody hanging, especially if the C language is new to you. It can be a little bit intimidating at first, and so that is why, for example, I recommend having the tutorial open, and then so when I'm learning any new programming language, what I will do is go through the tutorial, and I'll actually, so here we are on the repetitions, and it tells you what to expect, and it's got the example code. Well, yeah, the temptation is to just, copy this and then come over here and paste it in, and then, hey, you ran it. But I honestly, unless I look at the program and go, that makes complete sense, I'm just going to move on, I need to save time. Sure, that's valid. But if it's something that you feel unsure about, it really is better to, type your serial.begin. Of 9600. Because as you're doing that, it allows you to, and especially your students, to understand the code in a more organic way, and in a way that it basically sinks in better. And so to become empowered with code, to be able to use a particular programming language that's new to me, this is what I always do. I literally just delete the whole thing and start typing all the statements that are executable. I will sometimes leave out the comments. Other times, if I'm struggling with the code, I'll add comments of my own. But that's how I learn. That's how I would recommend that you get familiar with the language, so that you can provide the best possible guidance to your students. And that is the end of my sermon on that particular approach to learning. And again, please feel free to jump in. But I'll even gladly jump back to this if a question comes up for you later, or even if you want to talk about it after the session, I'm happy to answer questions on any coding concepts that might be a little bit still unclear to you. But hopefully that was helpful for kind of bringing out some of the Arduino language and its concepts. If it's everybody okay, can I get some thumbs up, thumbs down? Oh, you guys are awesome. Thank you. All right. All right. So opening the speaker notes here. Oh, let's see. Page 43 is where this comes from. And so we are now moving into the part where we're going to put all this together. And let's see here. What I'm looking for is my camera. Okay. So if I turn to page 43 in the handy dandy textbook that we sent out, we should have a picture of those things for you to dive into your box O parts and find. So if you turn to page 43, that way you'll have it handy so that if I move on and I'm talking about something else and you haven't grabbed everything completely, just have it on page 43, like that. There are two types of spacers. There's 1-inch metal spacers, and then there's 3/8 inch, or is that 1/4 inch? I forget. Half-inch nylon spacers. These are the shortest of the screws that you'll have available. And then these little nuts are nylon nuts. And then, of course, these are just the longest screws in the kit. And so, so one thing I did is I made sure to have an unopened kit ready to go. So here we are. And so basically go ahead and crack it open, and the things that you'll need, I'm going to bring out the bags first and set them out so you can see what the bags look like. And then going through so I think most of your goodies are going to be in these two bags. So this one has the shield in it on the left, and then all the screws and spacers are going to be in the bag with the wheels. So go ahead and break those guys open. And you can just pull out the sub bag that has the screws and washers and nuts in them. And be careful. There's a screwdriver in there, or if you have a scissors handy. Essentially, if you can carefully poke a hole in the bag with the screwdriver, that'll get it started. Otherwise, it's kind of hard to tear apart. And I try not to open it up too far because I don't want everything popping out. Well, actually, in this case, maybe that's a good thing. So many of you are probably just fishing around in your box and not seeing, but for anybody who looks up at your screen, you will see And I'm going ahead and grabbing the various parts that page 43 calls out from the. And then again, the 4 of the very shortest of the screws that are in that bag. The longer ones we'll be using later to attach the servo motors to the chassis.
So Andy, if I don't have the book, then where am I looking on the web version?
Oh, let me.
I was looking at assemble. I'm looking at assembly, but I feel like that's getting me to what we're doing for homework, which is like the chassis and stuff.
Yes, yes. Bear with me a second. I'm going to go back up to the beginning and get the PDF version of the book. Okay, so in the slide 4 resources, yes, copy link address, PDF book,
Okay.
and then I'll paste that into the chat. Paste. There. And so for that, page 40 will match the printed page 40. I'm going to take the rest of this and put it back in the bag so that I've got it for later. Actually, the gray bag that your Shield came in is a nice, oh, you know what? I want to use that gray bag for something else. No, actually I don't. I think the gray bag that your Shield came in, the Board of Education Shield bag, is a good one to drop all your extra parts into that you're not going to be using until later. Now, there is one, the design of the Arduino has changed a little bit. And so, oh, you know what? I didn't get all the parts. So you'll actually only be using 2 of the 3 long screws and 2 of the nylon spacers and 2 of the nylon nuts as opposed to 3. Okay, I think I've got everything. All right, so at this point, I'd like everybody to put their eyes on the screen for just a minute. Wanted to show you a few things about how this assembly goes. Okay. The way it works, and these are excerpts from pages 44 through 46. And what it's showing here is to put the long screws through the top of the board and have them stick out the same direction that the pins on the BOE Shield are sticking out. And then put your nylon sleeves over those long screws. Now, this this top corner one here, the one that's close to the corner, is not going to fit. So go ahead and skip it. Just add these 2. So I'll show you how that would work. Here's our Arduino Shield. And take this foam black thing off the pins. gently. So now you can see the pins that are coming out of the shield. And you can basically just drop 2 long screws through those holes that are kind of in the middle of the board. There's 2 holes in the middle of the board. Then hold them with your index fingers and turn the board upside down and put the 2 spacers on those screws. Then you've got your Arduino. Disconnect the USB cable from it so that there's no power while you're making the connection.
Busy today,
Yeah, my video just froze. I don't know if anybody can hear me. I still see. Okay, video just came back. Very interesting that just disconnecting a serial port causes the video to freeze up. All right, so hopefully you can now see that I've got my Arduino and my shield. And the idea is to put those sleeves over the screws, and then you'll want to get the can you see from the video how the pins line up with the holes in the on the Arduino? And so once you get everything lined up, the pins will mate with the holes, and the screws will also make their way through, though it looks like you'll have to take off the plastic protector that's underneath the Arduino. And then everything mates up real nice and it connects together. If you have difficulties, try it without the screws. So in that example,
So the
go ahead.
plastic protector has to come off?
If you're using the screws, I have to say that personally, I don't use the screws to attach the Arduino to the shield, but I can also tell you that in practice with students, they're not as gentle with electronics as I am. And so they really need the screws to hold the Arduino in place. So, so all of my robots don't have the plastic thingy removed, plastic shield. And so I just, get the pins lined up and then push it on. But it's a much sturdier setup if you, oh, actually I should, for that, I also want to emphasize that the Arduino should, will have a few pins, will have a few sockets that don't have pins sticking into them. So see how it says A5, A4, A3, and you've got pins sticking into each one of those. And then on the other end, there's an IO ref socket that does not have any shield pin sticking into it. Looking at the other side, you'll want to make sure that 0 through 7 all get their own pins. And likewise with 8 through 13 and ground and A ref, but SDA and SCL will not get pins. Yeah, it is a little tricky to get those screws through the holes and the pins all lined up, which is why if you feel at all in doubt, go ahead and leave those screws out. And just line
And
the
your
pins
experience
up.
with students is that they perform this relatively easily?
I wouldn't say relatively easily.
What age are we talking?
We're talking middle school and up.
Okay.
Although, you know, the text.
I guess they're more they're better than me.
Well, yeah, I mean, it's not easy.
I'm finding it challenging.
One thing about one thing about this entire kit is that they're going to be trying to follow instructions, and the student's tendency is to go more quickly than every step in the book. And sometimes they'll have to backtrack some. Yeah, I mean, I've seen classes that are 8th and 9th grade, but really I think the book itself is written for high school. That being, say, 9th, 10th grade and up. But yeah, I have seen a number of middle school classes use this as well. So I need to correct myself there. I'm sorry. I have seen a number of middle school classes use this, but the book itself was written for 9th grade and up. And so please don't worry about getting those screws in there if you're having trouble, because I'd rather just get the pins mated just right and move on to calibrating the servo motors.
Andy, is there any
One
issue
more
with using?
question.
Oh, sorry.
No, I was just going to ask if the plastic piece was, I didn't notice it's supposed to come off.
If you're using the screws, it'll need to come off.
I actually just threaded the screws instead of into the nylon nuts. I threaded it into the clear acrylic base.
Oh, Andy, that's amazing. I'd never tried that.
Excuse me, that's the way I have mine.
Huh?
That was my question.
That's
Was
exactly
will
the way
that?
I'm doing it.
Yeah, that was my question. Was will that like interfere when we go to mount this to the chassis later on?
No.
No.
Okay.
Because the
Perfect.
metal stands are longer. If you can see that
Oh, perfect.
there, that's going to mount on top of it. Just one suggestion.
Yes.
I get these plastic bins with lids that clamp on them, and they're different sizes. This is probably like $3 or $4 each, and that way the students can lock them up and the parts don't fall out, and you can use a piece of tape or some marker on it, so each kid gets their own, or 2 kids, because they're going to share. Each kid gets one of these buckets, and if they flail them around, the pieces are not going to fall out, because we would spend a lot of time just picking up resistors and jumper wires from the floor. So something like that is just a good best practice kind of idea that we had in my room. That way everything's in one bucket. Each 2 kids get their bucket, and they know where everything goes.
Yeah, and the dollar store has been a popular destination for those buckets. I've heard frequently that they're there. Walmart, of course, is going to have a better and more stable selection. Andrea, did you have a question also?
Well, that was my question, because I screwed it into the plastic base too.
Oh, perfect.
Right.
That's fantastic. All right. So let's see here. I guess I need to catch up with you guys now. So then the 4 small screws are going to go 1 on each corner. I really do advocate for a little bit of struggling on the student's behalf. I don't want to have everything be completely easy for them. And so getting those nylon spacers in just so during a lab session is not necessarily a bad thing. But if you have concerns, you can also in your instructions say skip the part with the 1-inch screws and the 1/2-inch nylon spacers. All that is, completely up to your classroom. Have we all got that? Seeing some nodding. I'm seeing, oh, looking good. Seeing some heads still down. So I'll give us a couple more minutes. When you get it together with the screws and the nylon spacers, go ahead and plug power back in. Or I'm sorry, plug the USB cable back in. And then
So Andy, looks like I'm missing 2 of these
So we
long
want all 4 of the,
spacers. Yeah, there's supposed to be 4. I only got 2.
ugh. Trying to think of anything we could do MacGyver wise to make sure that works okay for you.
Yeah, that I was thinking too.
You know what? I would
Can
say
you double up your other ones, like your plastic ones, instead of using them for the Arduino, just double up?
yeah, I mean, one way to do it might also be like a 1-inch screw and then just take one of the nylon nuts and but really for now I would say let's just go with 2 screws and 2 standoffs, and we'll have to make sure to get you some replacement standoffs. Also make sure to turn your kit upside down, and hopefully it'll turn up, but if it doesn't, we definitely want to get you some parts.
Yeah, I was just doing that.
Yeah.
Yeah.
I think
Well, I have a rubber mat too, so
that was the next thing I was going to say is, yeah, if it's sitting on a table without 2 of the standoffs, make sure that it's not a metal table.
right, yeah. No, it's on a rubber mat, so it
Okay.
should be fine.
Now, as you're building your robot, it will look kind of funny with just 2 standoffs holding that board up, but it also will work. My suggestion would be to put the 2 on the diagonal through the chassis when you get to building it.
Yeah, okay.
All righty. So next items that are actually, let's have everybody do a heads up for a minute. I'll just kind of show you what the students go through that we are going to be skipping or coming back to at the tail end. So you've got your nice little platform for prototyping. And so we talked to the students about how to connect a pair of wires together, and the rule for the white breadboard that's on your Board of Education Shield is that if you find a row of 5 sockets, you can put a pair of wires into them and they will be connected. You can even take a wire to connect 2 rows of 5 sockets, and then you can plug one wire in here and the other wire in over here, and they will still be connected. So there's a metal clip with some sockets sticking up underneath each of these rows of 5 sockets. And so when you put 2 wires in, they go into the same piece of metal underneath. And it has little springy grabber fingers that hold on to the end of the wire. And so, and then not connected would be if you don't have a jumper wire, like here's 2 separate rows of 5, you have wires going in and they're not electrically connected. Also, if you go anywhere in a row of 5 that's below another row of 5, those 2 wires are not connected either. And so this is actually the picture from the book. There's parts that we use to build indicator lights. One of them is called a resistor. It resists the flow of current, and it has 3 color bands for the amount that it resists, and a 4th color band that tells how accurate those 3 bands that tell you its resistance value are. And so in the example of 470, yellow is 4, violet is 7, and then this brown stripe, the 3rd stripe, is actually the number of zeros to append to that, those 2 digits. And so brown is 1. So we're going to add 1 to the digits 47 to get 470. And that's how to read a resistor. Then we talk about, hey, if you use a light, an LED light, like this one right here, it has a schematic symbol, as did the resistor. And the schematic symbol actually relates to the unique shape of the LED as shown, where the leg going into the triangle is indicating the longer leg of the the longer leg of the light emitting diode. And then the other end of that symbol is the shorter leg of the light emitting diode. It's like a one-way valve. So if you connect it properly, it lets current pass through. When you connect, say, a battery or some other voltage source to it, electrons will flow from the ground of the battery through the light, through the resistor, and then reconnect with their positively charged friends at the other battery terminal. And that's how it'll give off light. If you connect both to the same terminal, it won't give off light. We talk about voltage as being an electrical pressure that propels the current through the circuit. We also write a program after building a circuit to make the light turn on and then off. And then this is the program. I'm hoping to come back to this. And this is the circuit that they end up building. And it so happens that we'll be connecting our servo motors to these sockets labeled 13 and 12. And that's where the signals go to the servos. And these lights will actually serve as indicator lights. But they start just by connecting these lights and writing simple scripts to make them turn on and off. And we might be using this one instead, just to make it go quicker since it's a short course. And then after we talk about turning the light off, we talk about the timing and actually graphing that light on, light off behavior. And this is what's called a timing diagram. And it becomes important for any of the classes where it's the goal is to also understand the signaling that's going to these guys, which are servos. And these are the next items I would like you to grab from your box along with the battery pack. And so the servos are in the bag. Both the servos and the battery pack are in the bag with the chassis. Go ahead and open that up. And actually, you can take everything out of the bag, throw the chassis back in the box, That's this. And then we've got our battery pack, which can connect right into the Arduino. And then the servos, I'm going to bring up a slide for that connection. Welcome, whoever just arrived. There's the slide. Okay, so make sure that the little switch with 0, 1, and 2 on it is set to 0. By default, the little jumper should be set. There's a little, between the 2 ports, there's a little sleeve that's fit over 2 of the 3 pins sticking up, and it should be closer to the 5V label. Again, that's the way we manufacture it, so you don't need to worry about that. And then here is a close-up of how the servo cables are connected to those ports. And please note that the white wires are closer to the 12, 13 labels, and the black wires are closer to the breadboard. You could also look at it as these white wires should be closest to the edge of the board.
This isn't keyed in any way. It's just one of those things that students can put it in either way.
It's true that students can put it in either way. If they put it in upside down, it will not cause any blue smoke to emit from the servo. The servo just won't work until they catch the problem and fix it. Good question. The port, by the way, is keyed, but the servo plugs are not keyed, so they can get it in either direction.
All right, so 12, and then resistors.
So remember, the white wire should be closest to the edge of the board and to the numbers 12 and 13. And these are all things that almost all of them came out of the book. I think the only original work is that little how-to with connecting wires to each other is a little bit more terse in the book. Have any of you ever caused a lot of static electricity while you had earbuds in and you can feel little ticks inside your ears? I've only got it's kind of a wake up kind of experience. I just rolled my chair around and that the wheel across the carpet managed to generate some static that it delivered as current pulses directly into my ear. Okay. I'll be right back. After all that to do, I made about setting aside batteries. I didn't do that myself.
I gotta go get the book. Where is it? Here. Okay, so build and test. Shield lights and motors there. Okay. Connecting the servos. Centering the servos.
Yes, centering the servos is what we're going to be doing before we put our bot together. Last but not least, you will need that, I believe it's blue screwdriver that came in your kit. Right right here.
So go ahead and power up the board from the batteries as well.
Yes, go ahead and throw the batteries or connect put the batteries in the battery holder / pack, and then plug the battery holder's barrel jack into the barrel plug into the barrel jack on the Arduino, and reconnect USB. And then this is the
So
code you
the
will.
12 is 12 for the right side wheel.
Yes.
And 13 for the left. Okay.
Yes, that's exactly right. And we did try to do it so that, gee, since 12 is on the right side, it's going to be the servo connected to the right wheel eventually. And since 13 is on the left, it's going to be the servo connected eventually to the left wheel. And so minus the lights, we'll want your setup to look like this. Roughly. In contrast, mine is not quite as neat as it is in the picture. But both are equally correct. And I'm looking for the code so that since I didn't actually guide everybody through downloading the zip of all the pre-written code examples, I want to open it and send it to you. Let's see here. The code example is going to be named both servos stay still, and I'm going to paste it into the chat. And you can just from there copy and paste it into your editor. Okay, so here we are. Copy. Paste into chat. Oh, for some reason that went to just one person. Boom. I think we might have lost some indentation in the process. I'm going to try copying it from the chat and pasting it to my, oh, looks like it held up just fine. Hopefully that'll work as well in CodeBender.
Hey, Andy, do we have a brief description of why we have to center the servos?
Oh, yes, it explains it in the book as well. Sorry, I ended up kind of glossing over that idea. Basically, when you get to programming your robot to make maneuvers, you'll want it to be able to move forward and backward, but you'll also have programming statements that make it stay still. And to keep the coding as simple as possible, that becomes a number. So there's a number for staying still. There's a range of numbers for speed counterclockwise and a range of speed for clockwise. And right in the middle of that is 1500, which is the stay still value. And by the way, before running your program, go ahead and set your power switch, which is the 0, 1, 2 switch near the edge of the board. Set that to 2. You might see the servos twitch slightly, and you'll see a light come on by the breadboard and a second light come on by the servo ports, provided your battery's attached. Then go ahead and run the code. And so I'm running it now, and on my screen, you should in a second be able to see when the code finishes loading, both of my servos will begin turning gradually.
How many lines of code do you have? Because I think I might have some extra stuff left over. And I'm getting some errors, but how many total lines of code do you have?
Let's see here. 1, 2, 3, 4, 5, 6. But are you talking about printed lines or just total lines in the?
Yeah, like I cut and pasted everything in, but I have errors and I'm trying to figure out what I'm supposed to remove.
Okay. Let's see here. Let's look at the beginning of your program. Let's have the beginning of your program start with #include servo.h.
It looks like there's 22 lines.
Thanks, Ed. Thank you.
mean, but at least, but I'm using looking in CodeBender.
Yeah, file preferences. I think I can show line numbers here.
If you're if you take the zip file, if you just double click the zip line, it will pop right out.
It just
Yes,
says
that's
display, Andy, it says display line numbers in there. Go back into
They're
file
alive.
preferences.
thanks. They're alive, I heard somebody say. And then whoever is still wrestling with their code, how are you doing?
It's right in the middle on the left, right under compiler warnings.
Yeah.
Oh, there we go. Thank you. I remember it was in there. I just couldn't remember where.
So, what does it end on? Because I feel like I have old code in here. I'm in the CodeBender, so it looks different.
Okay.
I just need to erase some stuff. So I just need to know like how many total lines or what's at the end, where do I erase?
Okay, Control A,
Like, should
Control
there be a
V.
void loop at the end? And
Yes, there should be a void loop. Hopefully this is, can you see okay?
And there's an open,
Yeah, and then-
open
and then it-
curly and closed curly on 22.
on 22. Okay, thank you.
No problem.
Okay, Andy,
Yep, that's
Yes.
better.
the stuff that you pasted on the chat,
Yes.
okay, I'm getting 2 problems. And one is, I was wondering if that's the complete thing or if I'm losing something.
Well, we had another attendee who was either losing something or had too much. So are you in CodeBender or Arduino IDE?
I'm in the IDE.
Okay.
I know I have an issue because I'm on Linux. So
Oh, right.
so I was wondering if I have a carriage return line feed issue.
Oh, okay. Now, let me give you, can you quickly unzip a zip file if I send it to you? If I chat you?
Sure.
Yeah,
Okay.
I'm using the Linux as well. I'm running Linux Mint. So I unzipped it and that it dumped it right into the sketch editor, and that seemed to be working. And they started to spin, and I can tweak them. The only problem I'm having is that I think the connectors to the board.
Is this program both servos stay still?
Yes.
Yes.
I just pasted a link to the zip download.
Okay, because I unloaded that zip that you gave us earlier.
I don't know why I apologize.
okay. It came up
Okay, good.
in the, yeah, and it's looks normal.
Is the left servo supposed to be spinning?
Well, one or both of them might be spinning, if only for some reason, mine are spinning incredibly slowly. Here's what to do.
One of them isn't spinning at all. Good.
Yeah, I've got one that's not spinning at all, and then one that's spinning very, very slowly. And I'm trying to get back to
So
the
you have to adjust it.
yes. Okay, so do you see how one of mine is spinning slowly, the one on the left? Now, what you can do is there's a little hole right where the 3-wire ribbon goes into the servo case. And it's got a little Phillips screw in it. The device is called a potentiometer. And what you can do is you can adjust it. And if I turn it one way, it actually causes it to go faster. I turn it the other way and it slows down and stops and then goes the reverse direction. And so what you're going to do is use your screwdriver to search for that setting. And it's going to take a really light touch, but you want it to stay still. And then you can move to the other servo, assuming you're running both servos stay still, assuming it's running. Then again, very light touch, going back and forth, searching for that spot where it actually stays still, and also where you don't feel any vibration in the servo through your fingertips.
Yeah, question, Andy.
Yes.
On the servo plugs, how tight are they supposed to fit? Because mine are very loosely fitting, and they won't stay put.
Wow.
I had to push quite hard on mine.
Yeah, I had to push pretty firmly
Yeah.
too.
So
Mine are actually very, very
Okay.
soft. I mean, they will pop out with the
Yeah.
slightest touch.
Yeah.
then you're
Ditto.
not all the way in then. You're just touching on the end, you're gonna get intermediate, it's not gonna work all the time.
Yeah, I think Ed's hypothesis is something we want to try. Pull each.
I'm seated firmly. I can feel it go all the way down and hit, and it just floats back out.
Well, I guess the question then is on the under.
Okay. There they, okay, yeah, there they go. All
Okay,
right,
so Smokey, yours needed to be pressed down further.
press down firmly, firmly.
Okay, yeah, it does take some finger pushing. You
Yeah,
definitely feel it.
I didn't want to break
Okay, so it is
them, so,
a lot further down than.
yeah, so they,
Okay.
yeah, so they are seated now, okay. And I
Okay.
found the other standoffs. They were on my chassis already.
Oh, what a relief! That's excellent.
Yeah,
Okay, yeah.
Okay, so how are we? So has everybody run the program and adjusted their servos and gotten them to stay still?
Good to go.
All righty. Please jump in and say, hey, hold up. I'm not there yet, if you're not there yet.
not
Okay,
I
well,
quite
just
there
wanted to
yet.
mention, I'm gonna have to
Yeah,
leave.
still working.
I'm sorry, I have to cut out early.
Okay. Let's
So-
see. I will be sending, did you get your servos centered?
Yeah, yep, they're good.
Perfect. So what I'm going to do, just look up for a real quick second. I'm going to show you basically the homework is in the slideshow, and I'm going to send it to you as well. And all it is, will only take a second here. Okay, so basically we're going to put together our robot, and there's a list of pages in the book that I will send you. And every page is going to start with a parts list. and then it'll show a before and after picture of before assembling and after assembling. It'll call out what parts you want, and it'll have little instructions with check marks by them to tell you basically how we got from the left side to the right side. So we're going to have you go through all that. And when you're, and we'll also have you build a speaker and connect it to the breadboard. And when you're done, well, it won't look exactly like this, but it will look like this, but without the circuit on the breadboard up top, just the speaker that's here. So check your email for that and be ready to build your robot and have it completely built for Wednesday.
So you want it built before the session starts?
Yeah, we're going to have you do the assembly of the robot as homework now that we've centered the servos.
Good to go.
All right. So was that Andrea? You're departing for today? Okay, we'll see you. So I'm going to keep going. Oh, there will also be a YouTube link that I'll send you so that you can catch up on anything that you didn't see. Right on. All right. Okay. Have a good rest of your day, Andrea. And I'm just going to continue briefly and go over some informational stuff since we're doing a lot and skipping some parts. So here is the written instructions in the book for centering the servos. And those appear on page 64 of the book. Wherever possible, all of the slideshow stuff is coming straight out of the book because I prefer to avoid the secret knowledge that I'm only sharing with you. Although when it comes to assessment material, that is secret knowledge that we're sharing only with you and not the students. So here is a program I'd like you to try next, and it's going to be, let's see, it's a Servo Run Times, and I'm going to grab that from my code examples folder, and we'll have you try it out. And for those of you who have already downloaded the zip, it's called Servo Run Times. Servo Run Times. Opening it and getting ready to paste into the chat. And a few miscellaneous things in the homework, like I'm going to have you download the pre-written code since I forgot to have you do that before today. That really should have been part of your homework for today. And so sorry about that. So I went ahead and pasted the next code example into the chat. And it's that Servo Run Times. You can also grab it from the zipped folder if you've downloaded it. So go ahead and paste that into either your IDE or into CodeBender and run it. And what we want to see is your servos turning full speed clockwise for 3 seconds, and then your servos turning full speed counterclockwise for 3 seconds. And I don't know why, but I missed the closing brace at the end. Wow, I missed a lot. Let's see here. I may have not pasted in everything correctly. Give me another chance here. Paste this in one more time. It does not seem like it's keeping the loop part of the code. I wonder if I can give you guys a zipped file. Actually, hold on.
The downloaded zip file that you gave us if you unpack it, it works nicely.
Yes, it works very nicely. That one was on me. Unfortunately, I did not have you download it ahead of time. Let me give you the link to the zip again.
Just to check, this is gonna, both will run in one direction, stop, and then run in the other direction and stop.
That is correct.
Okay, so it's just the one and done.
I have a question.
Yes.
If one of my servers is sort of twitching to the left before they both start to go, does that mean they weren't quite as balanced as I thought they were and the servo stays still?
Yeah, that's a valid interpretation, but it's not what's happening in this case. Let me switch to.
I've got the same thing, Sarah.
Yeah, all of you should have that.
One of them starts.
Oh, I should have read the code before I asked the question. It was built in there. Or no?
Yeah, no, it's really fine. Please, we don't need to be in the learn everything that can. If you all learned everything you could from the book, we wouldn't be having the class in the first place. So what you're seeing here is when you turn off the power and then turn it back on, or maybe load the code. One of these servos, I think it's the left one, kind of twitches a little bit. Which servo did you say twitched?
On mine, it was the left.
The left. Okay. So the servo connected to P13?
Yes.
Okay. The reason for that is because there's a built-in light on the Arduino. I'm fishing for an Arduino that's not connected to a board. Okay, here's one now. There's a little built-in light that is by P13. I believe it's right there. Let's see if I believe that light right there is connected to P13. Oh my, I'm sorry, I unplugged it for whatever reason. Every time I unplug the serial port to the Arduino, the video from my document camera freezes for about 10, maybe 15 seconds. So I'm waiting for that to come back. I hope everybody can still hear me. Okay, good. Okay, my video just came back, and see that little light right there, this orange light? That light is connected to P13. And part of the Arduino's startup sequence is that it sends a high and a low signal to this light. And you'll see it flicker when it starts up. Well, unfortunately, those high-low signals are what also cause the servo to be controlled. And so it twitches just a little bit as a result of that. Did everybody get that zip file that I pasted into the chat?
Yes.
Great. So I'd recommend downloading that and then make absolutely sure to unzip it. So basically, if it's still in its zipped form, it's possible to navigate into it, but you won't actually be able to open it with the Arduino. So looking in my downloads, here's the tutorial code, Windows Plus. I am trying to zoom in so you can see a little bit better. Okay. All right, so the idea is to unzip it. Now, whether for you that's right click and unzip. So that's one way of doing it. Let's see here. Yeah, it's not showing, but the other way to do it is often to double click it, in which case some operating systems are going to unzip it, but Chromebook and Windows will allow you to navigate into it, at which point you'll find a folder and you can right click that folder and select copy, and then go back up a level, go up and out of the zip. And once you're back in your downloads, you can just right click somewhere in your downloads and paste that folder. Again, that's for Chrome and Windows. And then it'll unzip for you. And the reason I showed that way is mainly because that's the way that it works well in Chromebook. And so even though Windows and Mac have automatic things, Mac, you can double click it typically, and it'll just unzip it for you. And then Windows, you can right click and select unzip, or double click it, open, copy, back out of the zip and paste like I did just now. And so here is the ShieldBot code. And then the code that we're looking for is in chapter 2. And it's Servo Run Times. And so this is the one you can either file open in CodeBender. We should probably talk about that. Or if you have Windows Mac, you can probably just double click it and it'll open up into the Arduino IDE. And I'm not sure how it works in Linux. Okay, so here is here it came up in the Arduino IDE. And for any of you who are using CodeBender, I'm going to bring that up next and try to open it from there. Okay, in CodeBender, there's this hamburger menu, the 3 lines that look kind of like a hamburger on your right. And you can click that and select open. And it'll also let you browse into your downloads or wherever you unzipped it to. For me, it was downloads. And then basically ShieldBot, chapter 2, open both Servos Servo Run Times folder, and then Servo Run Times.ino. And so there it is, opened in CodeBender. And I'm going to try copying it from CodeBender to the chat, because maybe that'll work better than copying it from the Arduino IDE to the chat. So for anybody who has not had success with any of that, that's the funniest thing. For some reason, it just really will not paste beyond line 22.
It looks like there's a size of characters, or like a text message.
Yeah. Seems like that shouldn't be the case, but I will basically try removing all the comments and see if that gets us past a character limit. It's either a character limit or a hidden character. I think you're right about it being the character limit. At any rate, so how many of you have succeeded in getting your servos to go full speed clockwise and full speed counterclockwise? For those of you who have succeeded, oh, excellent. So you guys are really moving well. For those of you who have succeeded, try setting it, changing 1700 to 1550, and try changing 1300 to 1450. All right, so without any comments, paste. Hey, look at that. Okay, so for any of you who have not had any luck with the zip, the very most recent chat from me to everyone has the full program.
Can you
Give me
repeat the
those
changes
numbers
you
you want
asked
me
us
to
to make?
change again, please,
What were those
Andy?
changes?
Okay. So do you see on my screen?
Yeah, all right.
All
so
right. So let's try taking the left servo. And it turns out that speed control is actually 1500 plus and minus 100. So this right down here is stop, 1500. So if you want to go at half speed, try making that servo left. Instead of 1300, which is 200 below 1500, let's make it 50 below 1500. So that's 1450. And then for the left servo, instead of 1700, we're going to make it 1550. So that's 50 below and 50 above. And that should roughly be half speed.
So they're now not in sync. One's going faster than the other, then it's going to go backwards first.
Yes, yes.
All right, it works.
Excellent. So yeah, I want to emphasize that your speed control is 1500 plus and minus 100. So 100 would be, you can think of it as like 100%. Let's see here. I have a slide actually that will drive that idea home.
I think we had a robotics teacher uses the BioBot, and I think we remember something similar to that where it was numbering full speed, half speed, whatever. We had a chart similar.
Ah, yes, exactly. So you may have seen something, yeah, because basically the Arduino textbook is a rehash of the BioBot textbook, or an application, I should say. Just quickly under the hood, 50 times a second. The Arduino sends a high signal that lasts 1.3 milliseconds when it's 1300. It sends a high signal that lasts 1.5 milliseconds or 1500 microseconds when it's stay still. That's the 1500 for stay still. And then full speed counterclockwise, those pulses increase to 1.7 milliseconds or 1700 microseconds. Now, students get to learn this by taking a light, and instead of 20 thousandths of a second, they make it off for 2 seconds and then on for 0.17 seconds. And then they work incrementally down until they're sending the full speed servo signal. That's these brief, unseeable blink times at 50 times a second. And then this might be the table that you mentioned, where you're testing different speeds and directions with various numbers and filling in a table. And this is a close-up of the way the servo responds to those pulses. So if I make a pulse of 1450, I'm expecting roughly 30 revolutions per second. When you get to 1400, you're around 50 revolutions per second. So it's not perfectly 100%, but the best way to think about it is that 1400 is 100% clockwise, full speed clockwise. And if you really want to make sure you're full speed clockwise, go clear out to 1300 here. 1500 is 0. And then as you increase your pulse width, it starts going counterclockwise. And the wider the pulse, the longer that on time. the faster it goes in the counterclockwise direction. And again, 1400 to 1600 is where you have mostly linear speed control. After that, it flattens out and you're just basically asking it for everything it's got. Here is your homework. It's pages 77 through 85 and then 90 through 92. And again, all that is just following the instructions now that you have centered your servos. Oh, and very important all points bulletin. You want to physically unplug the battery pack from your Arduino when you're done with it for the day. The Arduino will continue to draw current even when you have that little 3-position switch set to 0. Doesn't draw very much, but after the weekend, your batteries will still be dead. So this switch goes to 0 when you're done, and then make absolutely sure to remove this plug every time you're not doing anything with the Arduino.
Andy, question for you.
Yes.
On page 80, it mentions about servo orientation and option 1 versus option 2.
Oh, I'm glad you brought that up. I'm going to have to open the PDF to get to that. Bear with me. Okay. Here's a file browser. And workshop. PDF. And that was page 80.
Yes, page 80.
Okay, so what he's talking about is the advantages versus disadvantages to where the servo output shaft is in relation to the okay, let's see here. Page 80, come on. Yes.
It's under chapter 3, assemble and test your bow shield.
Yes. So here we are. And see if I can zoom in. Can everybody see this okay?
Yeah.
Yep.
Great. All right. So this is what he was asking about. And for most of us at Parallax prefer to have the output shafts closer to the center of the chassis. And the reason for that is because there are a number of surfaces for which the trackball can actually have enough friction that when it's way out here, it makes it so that the front wheels that are trying to drive the robot slip when it's trying to drag that tail wheel around in an in-place turn. So that's the advantage of having the output shafts towards the center of the chassis like this. Having the output shafts towards the front of the chassis, the advantage of that is that those holes for centering the servos are here and here. So those of us who have gone with our higher performance approach of having the output shaft to the back, we actually tend to pop out the battery pack to get at the centering holes with a screwdriver because it's hard to get at them through the battery pack. Whereas if you have them in front, you can recenter them at any time. So this is mainly a personal preference thing, but for your robot, I would say mount them towards the center. That way, since you're experimenting with it, you can decide how you feel about, having the students, if they need to recenter their servos at some point, how much of a challenge is it going to be for them to unscrew the battery pack and remove it, which is going to be in this area right here. So do it like this, the one on the right, for yourself. and then just know that there is a valid other way. And if you don't have carpet, for example, it probably won't pull too hard on there's only certain surfaces that make it difficult for the robot to turn in place like this. So that is that. Are there any other questions?
I had one really quick question, if that's okay.
Of course.
Looked like you sent out some sort of email for the Learn information.
Oh, thank you so much for reminding me. I forgot. Yes. So you have been subscribed to our learn.parallax.com website, and that is where we keep our assessment materials. And so you should have an email in your inbox. Is it from Christina Stewart?
It's at no reply at Parallax. And
Oh, okay. Okay. Well, Christina is the person who set it up for you, but it came from no reply at parallax.com. And so learn.parallax.com is the site where I showed you, for example, the web version of the book is here, but also there's an educators tab. And in that educators tab, there are educator resources. And anytime we can make something public, we do. But assessment materials are the exception there. So if you come into the Arduino educators page, it's going to have some our most commonly used resources, and then strategy guides, standards matrix, the links to the textbook, and some scope and sequence are all public because they're not assessment materials. Then you need to log in to follow this link. And when you do, okay, so I'm going to take this off screen for a second so that I can log in. Without showing my credentials. Okay. So I'm not exactly sure if mine's going to look somewhat different because I also have privileges to edit the site, which you might not have. But so I'm not exactly sure how much of this will appear. But the main and most important difference is that when we go back to the Learn site, learn.parallax.com, now that I'm logged in, and what you should do when you log in is make sure to change your password so that the students don't use the one that's included in the email. Let's see here. We want to go to ShieldBot again. And then this is the educators. Whoa, forgot educators. ShieldBot. Okay, now there's a link to the assessment material. So this was not here before, and you can go in and you can download either all the question, exercise, and projects in one, or you can download them as individual chapters. So I'll go ahead and just try to be conservative and download chapter 4. I don't know how big it is, so or whether I'd have trouble waiting for it to download. But looking inside the zip, once it downloads, you've got a PDF and a Word doc version of summative assessment materials. So I think I just opened the PDF version. And the idea here is that there's stuff for the students to work through. And then after all that stuff, there's an answer key. So be careful if you're copying and pasting from this, make sure to copy and paste only up to the answer key, which is in red. And again, that's in both Word and PDF. So if you wanted to adjust it, it's in a Word document. And if you just need the materials and you want to print a certain part of it, it's there in PDF as well. And that is actually in addition, shouldn't have minimized that. That is in addition to PDF reader. There we go. That is in addition to practice questions, exercises, and projects that are at the end of each chapter. So if you look at a given chapter in the book, if you go to the end, there's questions, exercises, and the summary, and then questions, exercises, and projects. And these have solutions printed right in the book. So the students have practice that they can do here, and then you have a second set of that kind of practice stuff that you can assign to them or put in quizzes, labs, whatever works for you. So that is the answer about what that email from noreply@parallax.com is.
Can I ask one more follow-up question? I'm so sorry.
Of course, no, no need to apologize.
So it looks like these are fairly flat assessments. Do you have any recommendations as far as age group, if you're teaching high school, college, etc., or not really?
Well, we kept it generic. And yeah, I've seen teachers use, for example, a smattering of what's in there. For more advanced classes, it might be a few warm-ups. I mean, geez, I've seen a mechanical engineering class at CSUS where I actually looked at the questions after having, the project, and kind of winced and thought, man, that would be really rough. I mean, I'd have to spend probably a couple of full days working on that project to get it to go. On the other end, we have middle school and lower teachers who will take some of this material and actually condense it into single page handouts where they're saying, okay, what does a servo do? A, turn, B, sense light, C, etc. And so, yeah, I do apologize. I'd like to be able to make, a complete curriculum for each grade band, but that was a little bit too ambitious. And so what we did was we made general stuff available to get everybody to try to get the largest group. And then, yeah, if you need to tone it down or ratchet it up, that is definitely going to be why we have the Word document, so that you can hopefully take some of that and then up it to the level or drop it to the level that you need to. That's the best answer I've got.
No, it's fantastic. I was just curious about the target audience.
Yes. And then that is, basically your 9 to 12 for this book. But again, I've heard quite a number of middle schools succeed, but others where they're essentially, no, that's not at my kid's level. So it varies. It's really an important reason of why we're sending you the sample robot, is so that you can try it, you can get a feel for it, you can decide, if it works for your group. And then if so, here we are for the questions and answers. Okay, so we are at 4:15. I'm going to turn the recording off, but we can keep on going with questions and answers. Stop recording. Wait a minute. Before I do that, I just want to make sure I've got every last slide discussed, or rather, the most important of the slides. My computer is beginning to slow down. Okay, so you've got the idea of assembling the robot. There is also earlier on, starting on page 11, there's pictures of all the parts in case it calls something out that it's not clear what it should look like from that photograph. There are some nice clear photos near the beginning of the book. The all points bulletin I want to give you is when you're putting in the battery pack. This is where you use the nylon screws, the white nylon screws attached to the metal posts, the metal standoff posts that are currently making a little tabletop of your BOE Shield. So 2 of those posts that the BOE Shield is currently standing on are going to be attached through the chassis with white nylon screws here. So make sure to use nylon screws, not the metal screws here. Here's a picture of the speaker circuit and a quick little program to make sure it works. And then we'll be reconvening on this Wednesday at 2 p.m. Pacific.
Andy, one question.
Yes.
You said the nylon screws were an essential part of the standoffs here. Do you need a nylon spacer to make sure you don't have any conductivity at all, or is it just the fact that you have? Because I'm missing something in the understanding. Why?
Yeah, let me switch over to the
Oh, is it the
camera? All right. So I'm going to grab a assembled robot. Okay, so see this back post right here?
Yeah.
Okay. That post is attached to the chassis by a white nylon screw that passes through the hole in the battery pack, through the chassis, and goes into the post. And I'm going to grab that nylon screw.
And now that I see where it is, I understand why the nylon screw is there.
Yeah, and for those of you who didn't jump ahead in terms of why the nylon screw, the reason is, see these batteries right here? These, it's a very thin layer of plastic between the outside of the battery and the metal container, which is, gosh, I can't remember. It tends to be negative in alkaline and positive in rechargeable, or maybe that's vice versa. But at any rate, so if you have a metal screw that's come a little bit loose, it could nick the battery. And then when it nicks the battery, this chassis right here is actually connected to ground, to the battery's negative terminal. So what you have is a screw that might be conducting 3 volts with no resistance in the way, right down to the chassis. And so the battery gets kind of hot and it loses all its charge if you have the metal screw. So that's why we call out these nylon screws for there and there.
So it's not about the standoff, it's about the screw going through the battery case.
That's right, because on the front,
makes perfect sense.
Yeah, because on the front, I don't know if I can, there we go. So this is just one of those short little screws. The shortest of the screws is what's holding the standoffs on the front.
Got it. Makes perfect sense.
All righty. I'm glad you asked that before I stopped recording, but that's a perfect place to go ahead and stop the recording. And let's see here. So we'll see you all. You can keep on here, but 2 p.m. Pacific time on Wednesday, the 21st. Stop recording.